Okay, so for 6.4 part 1, we used the behavior of fluids slides that I made for you. The first question is, what is a fluid? So to answer that, we see a definition here. It's matter that flows. But let's watch a video. Let's see if I can get this video to work on here. And you don't really need the sound. You can see, kind of view it. But here we see there is matter that is a gas, and yet here you can clearly see that that gas is flowing. If you've ever watched fog for very long, you've actually seen the fog flow. It will go from, usually from a higher place to a lower place. It sinks. It'll flow down a river valley. So that's kind of cool. I want to show you guys that. So fluid is matter that flows. The next question is, what is an example of a fluid? Well, this has to come from your imagination, but what is an example of something that flows? You could say the syrup on your pancakes, or you could say the water down the sink. But you could also say, you know, the air coming off of the heater, right? So any solid, I'm sorry, not any solid, any liquid or any gas is a fluid. Okay, fluid doesn't just mean liquids; it also means gases. Okay, because it has the ability to flow. Next question is, what is Charles' law? And here we go. It is, as the temperature of a gas increases, its volume increases if the pressure is held constant. And we'll see what that means when we do the lab. But if you keep the pressure constant, increasing the temperature of a gas will increase its volume or its size. Okay. In other words, heated gases spread out, they expand, they get bigger. Here's an animated GIF of that. We can see we heat the gas and the particles move apart. Okay, so it needs more room, its size grows. In our own words, heating a gas makes it expand. Boyle's law. What is Boyle's law? Boyle's law says that as the volume of a gas decreases, that is the size, as the size of a gas decreases, its pressure increases if you keep the temperature the same, if the temperature is held constant. So let's see our little animated GIF of that. We can see that squeezing this gas, we keep the temperature the same, squeezing this gas makes the pressure go up. Okay. Remember from an earlier section, from section 6.2, I believe, maybe 6.3, that pressure is the amount of force that matter applies to something. So as we decrease the size of a fluid, it applies more pressure, it applies more force to this pressure gauge. And in our own words, we can say that squeezing a gas increases its pressure. We see that squeezing a gas increases its pressure. Next, we have Pascal's law, which is a different sort of law. And it says that when we apply a pressure to a fluid, that pressure is transmitted unchanged throughout the fluid. Okay. So Pascal's law says that pressure applied to a fluid is transmitted unchanged throughout the fluid. In other words, when you push on a gas or a liquid, that push gets spread throughout the liquid. Now, it's worth noting here that in the real world, fluids are compressible. And so when you push on a fluid, it doesn't immediately spread all the way to the other end of the fluid. If I take a folder and I start waving it around, it will push on the fluid in the room, and there will be a breeze on the other side of the room, but it won't be instant. It won't be instantaneous. It takes some time because the air in the room, it's slightly compressible. That's not the right button. Okay, so in our own words, pressure spreads evenly through a fluid. So question 9, it asks us to go back. It says, what happens when the size of a gas, what happens to the size of a gas when you increase the temperature? And this just takes us back to Charles' law. It's kind of asking us to look at Charles' law again. So when we increase the temperature, the size of the gas is going to increase. And question 10 it's interesting because it relates back to section 3, chapter 6, section 3. But it talks about the way that matter undergoes changes in phase or changes in state. So when we increase the temperature of matter, its particles are going to speed up and spread apart. Okay, so as they're heated, the particles of a solid are going to move apart. When they do that, it becomes a liquid. If we continue heating, they'll move apart even more, and it will become a gas. This will be easy to show you guys in the lab. I'm going to go ahead and do that. That's probably good. Make this container a little smaller so that they have to run into the ice here. Try to get this temperature as low as it will let me take it. Can't see the temperature because of my, to cool it way down here. We can see that the particles have almost stopped. Okay. If this were an ideal material, we would see that they would align themselves and make crystals, right? And we would have a solid here. As we increase the temperature of matter, so as soon as one of these particles runs into this fire, it might take a second. As we increase the temperature of matter, it causes the particles to speed up. That's what the temperature is. It's the average kinetic energy of the particles, or it's how fast the particles are moving. It also takes into account how massive the particles are. But the faster the particles are moving, the higher the temperature of the matter. If we increase the temperature a lot, eventually they'll spread so far apart. So now we have a liquid. Eventually they'll spread so far apart that they become a gas. And gases are less affected. So you see the pressure is really building now. These are the particles of a gas, and the particles, they run into each other and they run into the sides of their container until eventually they blow the lid off the container. So we're going to investigate this more when we get back to the lab. But as they're heated, the particles of a solid move apart and it becomes a liquid. As they're heated more, they move apart more and they become a gas. If you cool them down or lower the temperature, what you'll see is the opposite will happen. So what happens to the pressure of a gas if its size is decreased? Well, that's Boyle's law, right? As the volume decreases, the pressure increases. Okay, so the pressure goes up when you squeeze the gas. And if I apply a force to the gas, what happens? Okay, what happens to the pressure? Well, we know that the pressure is going to spread evenly. That's going to be Pascal's law. Okay. This brings us back to our lab. So we'll just take our lab from the beginning really quick. Behavior fluids lab. It says click laws. So laws. That's the wrong thing. Laws. It says click and drag the handle of the pump to pump some particles of fluid into the container. So let's use the red one for this one. The red particles are less massive. So the same particle is going to exert less pressure even with the same speed. Okay. I keep clicking the wrong document. Okay. Click and drag the handle of the pump. If any mistakes are made, we can start over by clicking the little doohickey. Drag the slider at the bottom to heat the particles. What happens to the particles as the temperature increases? Well, I think that what I'm seeing here, I think we're seeing these particles are speeding up. And if you increase the temperature of a fluid, the particles speed up. And they move faster. Which law does this describe? Which law does it describe where heating particles causes them to move faster? Well, we go back here. Heating a gas makes it expand. That's Charles' law. It's the same thing basically that we just read in our definitions, right? Heating them causes them to move faster. Of course, cooling them is going to be slowing them down. Okay. Click the reset button and put fluid in the container again, and then we're going to change the volume. So I'm going to reset it. I'm going to put lots in here for this one because it makes it a little clearer. All right. And then it says, click the handle to change the volume of the container. So we're going to squeeze this fluid. What happens when we squeeze a fluid? What happened to the pressure? Since we lower the, we increase the volume of the gas, we decrease the pressure. So it has like an opposite relationship, an inverse relationship. What happens to the pressure when we decrease the volume? Well, the pressure increases. Which law told us that changing the volume of a gas would increase the pressure? Squeezing a gas increases its pressure. That's Boyle's law. Number 9 says that when the container wall pushes on the particles, they collide and the pressure increases. Which law describes how pressure spreads evenly across the container? So we'll reset this and we'll view this, right? We'll make this as big as possible. We'll put lots of particles in here. I'll use the red ones because they're a little smaller. Put all the particles in here. Okay. Now, as I move the side of the container, we can see the pressure spreads out. The particles over here run into the particles here, which run into the particles here. And eventually that pressure gets pushed across because the particles of this fluid, they run into each other. If I push on the air, so if I swing the door of my classroom closed, I'll be pushing on the air in the classroom. Well, the air I push on, it pushes on particles of some more air. It pushes on air that's further this way, further this way, and further this way, until eventually that push from the door gets spread evenly through the whole classroom. That's Pascal's law. Okay. And number 10 asks us to experiment to see what happens when we change the number of particles, the amount of heat, and the volume of the container. I'm not going to summarize those findings, but I am going to play with this just a little bit to show you guys some of what this app can do. So you can put in some blue particles, put in some red particles. Okay. Right now we have a heterogeneous mixture. And as it stirs and stirs here, the mixture will become more and more homogeneous. See how the red is kind of down in this corner? Well, as we heat this, it's going to speed everything up. As they speed up, it'll mix more and more evenly. Okay. So now it's a homogeneous mixture, right? These particles aren't attaching to each other, but they're evenly mixed. And so if you were to look at this from the zoomed out view, this might look like, I don't know, a glass of salt water, right? The salt would be the blue here, and the water would be the red. I think in that scenario, I think water is a smaller molecule than salt. I'm not really sure. I'd have to think it out. But we see here a homogeneous mixture. It looks like a compound. It's not. Matter of fact, if we heat it enough, the salt will boil off. It'll come out the top here, and the water will sort of stay behind. I'm sorry, the water will come out the top, and the salt will sort of stay behind. That's not really what this app is designed to show us, though, so it's not going to show us that here. Okay. So we can cool it down and watch as the particles slow down and the pressure comes down. So the temperature of a sample is the average kinetic energy of the particles. The average kinetic energy of the particles. Sorry, someone's unmuted, and it sounded like they were doing a little bit of singing. All right, so that's it for our behavior of fluids lab. Okay. All right.